Hello, and welcome back to EECS 367, Introduction to Autonomous Robotics, and Robotics 320, Robot Operating Systems. Welcome to the fourth lecture of this semester, where we're going to be talking about dynamics, so physical dynamics and numerical integration for simulating the physical world. And so as we begin to kind of get towards the end of assignment one, right? So assignment one is going to be due this Friday. What we're going to start looking at now in the course is physical robot environments, right? So in assignment one, we were, which was our path planning assignment, we focused on this 2D world and trying to plan paths within this 2D world. But what we want to start moving towards is the ability to model sort of more realistic, more complex robots in the three-dimensional world that they'll exist in for them to be able to perform tasks for us. And so before we get into it, let me just go ahead and minimize myself. All right. And so when we talk about simulating our three-dimensional world, ultimately what it's going to come down to is our model of physics. And so on this title slide, what we're showing here in this graphic is one of the sort of famous stories from within the history of physics, which is the story of how Isaac Newton kind of conceived of the law of gravity that he ultimately proposed. And so in this story, if you're not familiar, right, as the story goes, an apple fell from this tree and sort of hit Isaac Newton, and that was the inspiration. And so it does get at this point of kind of like this interesting part of the history of science, which is oftentimes that there's sort of two stories that kind of come about, right? So there's the formal story, right? So you could go back to Newton's Principia, where the formal proof, right, and the formal kind of work is laid out. And then we have, on the right-hand side of the slide, right, we have this sort of caricature, this sort of story that goes along with how, science and advances in science are often inspired. And so if you're interested, it is sort of an interesting story to read up on. And so there's speculation even still about the story of the apple. And so if you're curious, it is kind of a fun sort of tangent to go down. But for our purposes within robotics, right, so the work of Newton and Euler and many other physicists ultimately is what enables our physical simulators, our dynamic simulators to work and to be very successful. So in the video here, what's being shown is the Kuva robotic lightweight arm being operated within a physical simulator environment. So in this case, it's the VREP simulator. And so what's included in this simulator, and the reason that it's very successful, is that it can model the physical dynamics of these rigid body objects, including the robot and the objects that the robot is acting on, in a very realistic kind of high fidelity manner. And so that's one tool that roboticists have in order to enable these systems to be effective, right, in the physical world, because you can essentially model them in simulation, you sort of train models in simulation, and then apply them in the physical world. And because your model in the simulator was realistic, ultimately the system that's deployed in the physical world should be effective. And so if we go back to our robot operating system framework and look at how dynamic simulation fits in, right? So where dynamic simulation fits in is really within sort of that lower level hardware component. So in particular, the reason that we use simulation is because we want to be able to simulate the sort of expensive or the difficult to manage physical hardware components, right? And so, or potentially to speed them up, right? And so this is where simulation fits into our robot operating system framework. And so on top of this simulator, then we can build on the applications and the kind of core modules of our robot operating system that we're interested in studying for this particular course. And so if we go back to those modules and ask once again what it is that we're going to be focusing on. So here's the slide that we talked about during our first lecture this semester, where we considered the various components that a robot operating system would want to be able to support, right? So the kind of core functionalities that a robot application would want to be able to use and interface with, while kind of ignoring those low-level hardware details. And so highlighted in red and blue and green are the projects that we're going to be considering in this particular course. So path planning, right, that one we covered in lecture 2, and you're beginning to wrap up with assignment 1. This particular lecture is on dynamic simulation, so on the right-hand side of the figure. And then coming up in next lecture, right? So next week we're going to be talking about feedback control, and so together these first few projects are we're sort of building up the foundation of our robot operating system, so that by the end of project 2 we'll actually be able to control a physical pendulum arm within a dynamic simulator. All right, and so to start looking into dynamical simulation in more detail, here's a question I'll pose to you. So I'll give you a moment to think about, just to kind of get us thinking, right, to get us started. And that is, we've got this image here on the slide. What do you think we might be trying to convey with this image, which is sort of, to give you a hint, is maybe bringing together, two worlds. And so I'll give you a moment to think about it. All right, and so you may have come up with the answer, but so we've got this portrait of Beethoven and this image of Debussy, right? So two classical composers within an auto mechanic setting or workshop. So what we have is classical mechanics, and so this is just sort of to kind of get us thinking here, right? A little bit of brevity, and so when we talk about dynamical simulation, right, we're talking about how we can simulate the physical world. And classical mechanics gives us a set of physical laws to describe our physical world. And so in particular, there's two key components of classical mechanics for describing the world. And so the first is that it's a set of tools that allows us to describe the motion of objects, or what we might call like object bodies. And then secondly, it's the ability to describe this motion based on forces that act on the object bodies. And so within robotics, we focus really on those two components of classical mechanics. So the first, right, this notion of motion of object bodies, we refer to as kinematics. And so kinematics is essentially this concept that objects can take poses within space. They can take orientations within space, and that idea that their motion in space is captured within kinematics. Secondly, then, we have this idea of forces acting on these object bodies. And so this is what we refer to as dynamics, right? And so dynamics describes this idea of motion over time, right? And so to summarize the distinction between these two pieces of classical mechanics, we could say that kinematics describes the geometry of motion, right? So it's this idea that there's a possible set of poses, a possible set of states that our robot or our object can be taking. And then dynamics describes how those states will change over time as they're acted on by forces. So to look at this kind of in a concrete example, so I'll play this video. It's a short clip that shows these two ideas separately. So we have these skeletal structures which are in simulation, and I'll point out, so the figure in black, so it's sort of towards on the left-hand side of the video. This figure is showing data that was captured from a motion capture system. So it's essentially just replaying the set of poses that an actual human being was taking over time. And so it's just this playback of pre-recorded kinematic sort of data capture, right? And so it doesn't take into consideration any forces acting on the human. It's just recording the poses that the human was taking to illustrate this idea of kinematics. Whereas the other three figures are skeletal structures that are being simulated with dynamics within the simulation engine. And so what you'll see with them is that they'll actually react to forces within the environment. So as we start to play this, as these sort of objects are thrown at the simulated skeletons, you're seeing that they're reacting to those forces, right? So the motion of those structures is being affected by the forces in the simulation, whereas the kinematic structure, was not affected. All right, but before we look into trying to create our own simulator for such a sort of complex scene, let's start with a slightly simpler example to really kind of fully understand this topic of dynamic simulation from the ground up. So the particular example that we're going to be looking at and focusing on is a motorized pendulum. And so you may be familiar with this from maybe some physics background, but we're going to kind of look into this with some more detail. So within this figure, we have this this single pendulum shown, and so the basic state of this system, or the sort of setup here, is we have a point mass m that is extended away from this axis of rotation at a length of L. And so in this case, L is shown to be of length 1. And in addition, this pendulum can swing about that axis of rotation. So the angle that the pendulum has swung at any particular instant in time is going to be expressed as this theta with respect to the vertical dashed line here. And finally, then we have the torque term. And so the torque term is what's going to describe our motor and the effect that the motor has on the pendulum as an angular force being exerted at that axis of rotation. And so this right-hand side sort of is describing the system in term, like kind of completely, right? So it's kind of completely giving the state of the system, whereas the actual dynamics of the system are going to be described by an equation of motion. And so that's then shown on the left-hand side. So once again, if we look at these from these two kind of perspectives, we have the dynamics on the left-hand side and then the kinematics on the right-hand side. So within the dynamics, it's this equation of motion. So it's describing how forces are going to affect this object over time. And then on the right-hand side is the sort of set of states, the set of configurations that the system can take, right? And so the kinematics describes this system level, whereas the dynamics describes the actual change of the system over time. All right, so let's break this apart, and let's start by really looking into what we mean by the state of a system. So within robotics, one of the things that we have to do is we have to be able to describe, physical objects in space. And so to do that, we consider the state to be comprised of a set of what are called degrees of freedom. And so these are essentially variables describing the particular configuration of an object at an instant in time. And so these usually, in the context of robotics, these are describing translational degrees of freedom or rotational degrees of freedom for the particular links or joints that make up a robot. And so in this particular figure, for example, this is looking at an airplane, and it's illustrating this idea that there are 3 degrees of freedom for rotation within an airplane, right? So you have the roll, the pitch, and the yaw, which are each distinct in how they will affect the pose of the plane at each instant in time. But in addition to these 3 degrees of freedom, there's another 3, which are the translational degrees of freedom, right? So the translation describes where in space the actual sort of origin of the plane is going to be centered, right? So the translation describes where in space the origin is going to be centered, whereas the rotational degrees of freedom then describe how the orientation of that plane is going to be configured with respect to the origin that it was translated to. And so in our example pendulum that we looked at on the slide before, in that particular case, right, we have a single degree of freedom, which was just a single revolute joint that our motor would be acting on. And so in that particular case, it's a relatively simple state in order to define, but we can use this same concept of degrees of freedom to represent the state of more complicated robots. So, for example, on this slide, we could consider some humanoid robots, and the skeletal structure that's described by the corresponding degrees of freedom within that humanoid structure, or we could consider larger, more articulated robots like the PR2, for example, which is shown in the lower right hand corner. And so once again, these robots could be described in terms of their state, which is itself a collection of degrees of freedom. And so to get a little bit more into the details here, so when we talk about degrees of freedom, one of the things that we're really describing is how a robot is comprised of a set of rigid body, what we call links, each of which is defined within its own coordinate system, which typically we'll refer to as a coordinate frame, or sometimes I'll call it a frame of reference. And so within that, then, using these rigid body links, a joint within the robot structure is what connects 2 distinct links, right? So 2 distinct rigid bodies are connected by a joint. So, for example, in a hinge joint or a rotational joint, you have 1 degree of freedom. So as shown in this figure on the lower right-hand corner, it's this axis of rotation that connects the two then rigid bodies together. Another type of link, there's a few other common types of links that we see in robotics, especially prismatic joints. So prismatic joints are what enable translational motion between two rigid body links. And then sometimes, although it's less common that you see these, but you could consider ball and socket joints. So this is similar to, for example, like the human shoulder operates similar to a ball and socket. And so each of these then different joints within a robotic structure would get actuated by a motor. Right? So the motor would apply some force along the axis of articulation, and that force is then what would cause a transformation among the rigid body links. And so we represent these transformations based on what are called linear transformations. And so as we move forward in the semester, when we get to forward kinematics, we'll be looking more into details of those. But the key takeaway here is that ultimately our robots are made up of this collection of rigid body links and articulated joints. And so let's look at some examples from physical robots of how these systems are built. So one thing to note is anytime we have a robot, it's going to be comprised of n joints and n+1 links. And so this kind of guarantee follows from the fact that a joint in our framework directly connects two rigid body links. And so following from that, we can make this statement that there will be n joints and n+1 links. And so for our purposes in this class, we're going to be considering the joints and links that form a tree hierarchy to describe the robotic structure. And so the tree-based robotic structures that we'll be considering for this course, they won't contain cycles within their kinematic structure. So they'll always be sort of what we call open chains. And so within this tree structure, we'll call the root of the tree, which will be a link, we'll call that as the base link for the hierarchy. And so in addition, within this framework, each rigid body link will have only a single parent joint, but it could have multiple kind of outgoing child joints. And so if we ever use the phrase like a serial chain as the robotic structure, that's a robot in which every link has only a single child joint. So for example, the two robotic structures shown on this slide would each be serial chains, since as you walk through their kinematic structure, you'll note that each of the links is only connected to a single joint, where each of the joints would be one of the actuators that's built into the robot. All right, so let's look at a few more concrete examples of robots and consider how they fit into this notion of a kinematic structure that we've been discussing. So to start, let's consider a planar robotic arm. So this particular example comes from this really neat Icon 2 project that was used to actually draw portraits of humans. So in this particular video, what you'll see is the robot arm drawing out the lines to make up ultimately a portrait. And if we focus in on the robotic arm, what we could notice is that if you ignore the wrist, which is actually controlling the pen to paper, the remaining portion of the robot is actually a two-link arm. And so it's actuated at the base of the chain, and then it has that kind of elbow joint midway through the chain. And so those two joints then make up what we could consider as a 2 degree of freedom arm. And so in this figure, we're taking a bird's eye view of the two-link arm and a kind of conceptual model so that we can kind of fully observe the robot's configuration. And so if we look at this robot again and consider what the state of the robot can be represented as, so we'll first note that we have 2 rotational degrees of freedom for this two-link arm. So the first degree of freedom being theta 1, and the second degree of freedom being theta 2, as shown in the figure here. And in addition to these two, we also have 3 rigid body links. So link 0 being the base frame shown at the origin, the second link being link 1 shown at that middle revolute overlapping with the sort of middle revolute joint, and then the end effector link being shown here, link 2. And so collectively, these rigid body links and the associated rotational degrees of freedom then describe the state of this particular two-link arm. So another example of a real robot that follows this kinematic structure is the SCARA arm. So once again, this is an arm with two revolute joints forming the two-link arm portion of the robot. The one modification then on the SCARA arm as compared to the example on the previous slide is that it has this translational end effector that allows it to do grasping tasks within its workspace here. And so while this is sort of a step up from that two-link arm, robot structures can get even more complicated. And so, for example, with the fetch robot, illustrated here are the revolute joints and also the links that make up this fetch. And so not only can this fetch articulate its set of revolute joints along the arm portion, but in addition it can elevate and move its torso. It can also rotate its entire base and translate its entire base within its environment. And so it's a more complicated kinematic structure, but at a high level, it follows that same representation of the state space being a collection of rotational and translational degrees of freedom in relation to the rigid body links, right? And so oftentimes we can kind of separate these two, and we can consider first of all just the rigid body links, which would be kind of notated on the left-hand side of this figure, and then in conjunction we can consider each of the links, or each of the joints that connects the various links and allows the robot to actuate within the environment. And so a demonstration of the fetch actuating within the environment is shown in this clip here from our lab, where the fetch is being used to serve these boxed waters. And so you can see the base moving here while its arm is moving, and it is able to actuate and manipulate the objects within the scene. But this particular fetch is not very very human, you might say, and so there are also humanoid robots. For example, the Atlas robot shown here. So the actual physical robot hardware is shown on the left-hand side, and then an illustration of the various links and joints is then shown on the right-hand side in this particular case. And so one use case of the Atlas robot was from within the DARPA Robotics Challenge, where here there's some example results from that particular challenge of the Atlas robot within simulation. And so in this case, this is based on the gazebo simulation framework. And so you can see that the Atlas robot is able to move within the environment in a using its human-like set of links and joints. And here it's attempting to drive the car towards a goal. All right. So you may be asking then why it is we would want to be simulating robots, right? Or sort of what are the reasons for our focus on simulation? And so it's a good question. And so the two sort of important answers for why it is we would be simulating robots is, first of all, the fact that robotic hardware is extremely expensive still. And so if you implement a controller that has a bug or that is not sort of optimal, then it's possible that you'll break your physical robot, which will be a sort of a substantial economic cost, right? In contrast, working within simulation is extremely inexpensive in comparison, and so this allows us to sort of iterate the development cycle much faster and much more economically. In addition to that, the other reason why simulation is useful is because it can actually be used within robotic frameworks as a means of control, right? So for example, optimal control policies could be defined based on the output of a physical simulator. One other reason why simulation is useful for roboticists is that currently robotic simulation frameworks are readily available, And they're built on top of physics engines which implement numerical integration for dynamics simulation. And so one example of where these physics simulators are useful within robotics would be this NASA Valkyrie robot. So in this clip, you'll see the NASA Valkyrie robot walking within its environment. And so this is a physical robot here, so this is not in simulation. However, this particular robot and the controllers that are being used on it were developed within simulation. And so if we look at that same robot and how some of the development for that could have looked, an example would be shown here. So once again, this is a clip from within the Gazebo simulation framework, where you can see the controllers are essentially being implemented and tested. And initially, the controllers are not very good, right? And so the benefit of simulation in this particular case is that it allows this testing and this development of the controllers and the underlying robotic mechanisms without causing physical damage to a Valkyrie robot, which would be on the order of hundreds of thousands to millions of dollars in the physical world. And so this serves as a great motivation for why simulation is popular and has great use within robotics. So this now brings us to our first robot that we will be implementing, and so this is what we call Pendulum, and so it's for assignment number 2 or project number 2, where we're going to be implementing the model, the physical simulation of, and then the control for a 1 degree of freedom robot arm as shown here. And so this should look somewhat familiar to the one-arm pendulum, or the one-link pendulum, which we discussed towards the beginning of lecture on this slide. And so in particular, in order to make this system work within simulation, what we're going to be focusing on is the equation of motion for the pendulum. And so I'll point out that for us to be able to ultimately control this pendulum, so to have it sort of approach a desired state, theta, we'll need to be using the motor torque in order to actually actuate the arm. And so on a physical system where this notion of motor torque might be sort of familiar, and it's certainly nice as a sort of illustrative example of how motors are implemented within robots, is this example of a stepper motor from a snap circuit. And so what you'll see here is Professor Jenkins is going to modify the resistance that's applied to this particular motor. And so as he decreases the resistance, it will increase the current that's sent to the motor, which will result in an increased speed of the actual kind of actuation. And then as Professor Jenkins then increases the resistance, which will happen in a moment here, that will then decrease the current and therefore decrease the resulting speed of the motor. So in terms of what this then looks like in a sort of more realistic setup for robotics, so it starts with that motor, but typically what we'll be using within robots is what's called a servo motor. So within a servo, there's the actual electric motor, which is the actuator, but in addition, there's a few other tools that help for actual control tasks. So first of all, there's typically a proprioception mechanism implemented within a servo, and so this is what allows us to essentially perceive or sense what the state of the motor is at any given time. So one way to implement this proprioception would be through an optical encoder, where you keep track of what angle the motor has been actuated to at each instant in time. In addition to that, servos will also typically be integrated with a control circuit. So one example is shown here, this 4-channel H-bridge. But this is just sort of a high-level overview of servos, right? So for this class, it is a software-based class, so we're not gonna go much more into the hardware details. But as an overview, this servo background can be useful. So to consider, another example of servos in action, so to speak. One class that you might be interested in looking at in the future is Robotics 550. So to give an example of some of the projects that students have worked on in this particular course, so here you can see students implement what's what's referred to as an inverted pendulum. So in this particular case, they have a controller implemented that's designed to keep this two-wheeled vehicle upright. And you can see that despite the students sort of interacting with it and introducing additional forces, their controllers are able to actually stabilize the vehicle and keep it from falling over, which is really quite impressive for a controller. And so in terms of what it is we would need to actually kind of keep these systems operational, it comes back to that equation of motion. So in this case, our equation of motion for the pendulum system is shown on the left part of this slide, and it has three real components. So on the right-hand side, we have net force, and then on the left-hand side, we have the inertia multiplied by the angular acceleration. And so we can think of this as following the same form as Newton's second law of motion, which was defined to be F equals ma. So force is equal to mass times acceleration. And so if we look at this acceleration term, just to kind of point out that this is the angular acceleration. And so you can think of this as being the second time derivative of the angle of the pendulum, right? So alternatively, we could say that this is the rate of change of the velocity of the pendulum angle, or the rate of change of the rate of change of the pendulum angle. And so these forms then are equivalent. So you might be asking then, how was this equation of motion derived? So it's important that we at least briefly cover this to give some context as we begin to implement our simulators. But to do that, we'll have to review a little bit of math just to make sure that we're all on the same page. So to begin with, let's consider this derivative, this idea of a derivative. And so when we're talking about derivatives, what we're really talking about is rates of change. And so in this particular case where we have d theta over dt, this is describing the rate of change of the pendulum angle theta with respect to the variable for time t. And so implicit within this representation is the idea that the pendulum angle theta follows this function which we could call f, and that function f is a function of the time variable t. And so while this is the implicit assumption made about our pendulum angle, this notion of a derivative is a more general concept within calculus, and so we could really consider a derivative for any function f with respect to some variable which we could call a. And so to pick a particular example, so we can build some visual intuition about what derivatives and these rates of change really kind of represent. Here on this slide we have picked some function f, which is a function of the variable a. So on the horizontal axis we're plotting that variable a, and then the vertical axis denotes the value of the function evaluated at each point along that horizontal axis. And so what we want to do now is build some intuition about what a derivative is representing in a visual sense. And so to do that, right, so since it's a rate of change, let's sort of start by picking some point along a and evaluate the function at that point. So here you can see the point that we've picked. And so now what we want to do is we want to understand what is the rate of change of this function at this particular point. And so one way that we could kind of move in that direction is by sort of shifting along the horizontal axis by some step, which we've called here h, and then reevaluating the function at this new point, right? And so once we have these 2 points, then we could ask, well, how did the function change when we how did the vertical axis essentially change as we stepped along the horizontal axis? And so to visualize that, you could imagine drawing a line between these 2 points, and then the vertical displacement here, which we've described with delta f of a, is denoting that change in the function value across this horizontal step. And so what a derivative then is representing is the slope of this function as that step along the horizontal direction gets infinitesimally small. Okay, and so the way then that we would notate this is by saying, for example, this f prime of a, right? So the derivative of the function f with respect to variable a is the limit as that horizontal step goes to 0 of the difference between the function f evaluated at the stepped position versus the original position at point A divided by that horizontal step. And so while this is the notation for a derivative that Lagrange used, there are alternative notations that you might see. And so, for example, there's the Leibniz notation, which we talked about, or we were using on the past few slides. And in addition, there's Newton's notation, which we were using with respect to the pendulum angle. I think it was 2 or 3 slides back, where you have the dot on top of the variable. But all 3 of these notations are referring to the same concept, which we just talked over. And so if you see these different notations throughout this course, or if you're reading external sources, you can remember that they're referring to the same concept of this rate of change that we talked about. And so one brief divergence, or one sort of brief tangent I want to mention is back to this idea, or this tangent about LaTeX math. So I mentioned this briefly, I think it was last lecture, but it may have been 2 lectures ago. So just a reminder that if we're responding to things over Slack, we might, we in the course staff, we may respond in this LaTeX notation, which is a formal TypeScript used commonly within academia or for formal mathematical proofs. And so, for example, if you wanted to describe the notation shown on the lower portion of this particular slide, you could do that using LaTeX, which is shown on the upper portion of this slide. So this might be useful for your reference if you start to look into LaTeX, or if you want to express any of these equations in Slack in a way that will kind of be unambiguous for the course staff and your fellow students. All right. So back out of the tangent then. So if we look again at this first derivative, which we talked about, you might then be asking, well, how does this relate to that notion of a second derivative, which we saw with the pendulum's angular acceleration? And so the concept really extends rather naturally, right? So if we think of the first derivative as itself being a function of a variable, then you can sort of take the derivative of that function a second time, right? And so you essentially just substitute in the first derivative as a function within the calculation for the second derivative, which is illustrated on the lower half of this slide. So differentiation then, to sort of summarize, is this process of finding a derivative for a particular function. And so we showed how to do that visually by looking for the slope of the function at a particular point. But in terms of being practical for calculations and computations on our computing devices, typically the process by which you will actually be able to implement these concepts is for functions that are in what's called closed form. And so for these types of functions, for some of them at least, there are rules for differentiation that we can implement. And so you might be familiar with, for example, the power rule, the product rule, the chain rule. These are common tools that are used to help with our calculations and make them much simpler and actually possible to sort of implement mechanically. All right, so in addition, right, so if differentiation is this process of finding a derivative, there's an inverse operation, which is referred to as integration. And so integration can be thought of as performing a sum for the area beneath a function. And so here on the lower portion of the slide is an example of how these two concepts relate, in kind of formal notation, but visually then on the right column, we have these two different plots, which are useful just as reminders for your reference as these two topics come up. All right, and so the next sort of brief summary then is how this concept extends to functions of multiple variables, and so this is where differential equations comes into the picture. So, for example, if we had a function, let's say z equals f of x, y, t, right? So the function f is now a function of 3 variables, and if 2 of the variables, let's say x and y, are also dependent on this on this independent variable t, then you might want to be able to ask a question such as, what's the partial derivative of z only with respect to one variable t? And so we would write it as shown here, where we have del f divided by del t. And so to actually work through this, the one way to think about this is to essentially use that same concept of a derivative that we talked about before, but just where we treat x and y, the variables x and y, as constants. And so this would be one approach for taking the partial derivative, or one way to think about that. Alternatively, then, you could also ask for what's called the total derivative of z with respect to t. And so to calculate this, you could use a tool such as the chain rule for the calculation. Okay. And so another important tool that's just worth kind of briefly remembering is some of the concepts that you may have seen from trigonometry, and in particular, we just want to briefly bring this up so we can point out a few useful functions within JavaScript. So for these trigonometric functions, you can refer to the math library in order to have these be calculated. So sine, cosine, tangent, arctangent. These will be useful for the implementation of the pendulum, where, for example, the sine function is used. So if we come back to the double pendulum and the equation of motion for the double pendulum, we had this question before we went and reviewed some of the calculus, which was basically, how was this equation of motion actually derived? So let's go back to our pendulum diagram, and let's look at this equation of motion. So where this equation of motion actually comes from is what's called Lagrangian mechanics. So a Lagrangian is the term defined within that red box at the top. So it's defined as the kinetic energy of a system minus the potential energy of the system. And using this Lagrangian term, the equation of motion is defined according to the equation below it. So if we take these derivatives of the Lagrangian and we set them equal to the motor torque of our pendulum, this then is how we can derive our equation of motion. Right? And so then, just as a reminder, right? So these terms del Lagrangian over del theta, that's specifying the rate of change of the Lagrangian with respect to one of the degrees of freedom, which it would be theta sub I. But just to remember, right? So for our pendulum example, there is only one degree of freedom, right? Which is just the single, revolute joint with an associated angle theta. So we won't use the subscript in our implementation. But if you have a system with more than one degree of freedom, the Lagrangian extends to handle those multiple degrees of freedom. Okay, and so now let's kind of walk through how it is we can derive this equation of motion in this way. And so to do this, right? So since the Lagrangian was defined as the kinetic energy minus the potential energy, we have to first define what the kinetic energy and potential energy of this system is. And so from high school physics, we can remember that the kinetic energy for this system is going to be 1/2 the inertia multiplied by the angular velocity squared. The potential energy, meanwhile, is then defined below that, right? So we have U being equal to mass times the acceleration due to gravity times the length of the pendulum multiplied by 1 minus cosine of the pendulum angle. And so using these two terms, then we'll actually be able to derive we can then define our Lagrangian, and then using this we'll step through how to derive the equation of motion. Right. So let's take our Lagrangian, and let's take that general form of the equation of motion to the next slide, and let's step through this derivation. So let's start with this first partial derivative of the Lagrangian. And so for this partial derivative, right, so it's being taken with respect to the pendulum angle. And so if we sort of step through this, right, so the first thing that we can do is we can look at what is the derivative of this first component of the Lagrangian with respect to the angle theta. And since there is no variable for angle theta in this first component, the first term is going to differentiate to 0. And so just to point out, right, that's because this is inertia multiplied by the angular velocity. So the angle itself is not a variable there, right? So the next term then, so if we look at what is the derivative of the remaining portion, all right? And so if we step through that, we can use an identity for the derivative of a cosine to ultimately arrive at this value, which is negative mass times gravity times length of the pendulum times sine theta. All right. So that's one component of the equation of motion that we've derived. And so if we step through to the next one, so now let's look at what the partial derivative of the Lagrangian is with respect to the pendulum velocity. So in this case, the first term does not differentiate to zero, but the second term does, right? So the second term in this expression doesn't depend on the variable for angular velocity, so that will differentiate to zero, but the first term does depend on the angular velocity, and so if we apply the power rule, we can ultimately calculate that this differentiates to inertia multiplied by the angular velocity. And then finally, we have that final ddt that we want to apply, right? So if we take ddt of the inertia multiplied by the angular velocity, the inertia is a constant, so we can pull that out, and we're left with ddt of angular velocity, which is itself angular acceleration. And so, using those two terms now, we can plug them back into our equation for motion, and we'll have arrived at our pendulum's equation of motion that we've been showing on the pendulum slides, and so that now that steps through the derivation. So one theorem that we can recognize is applicable in the case of the pendulum is what's called the parallel axis theorem, and so what this theorem states is that when you have a point mass rotating about a fixed axis of rotation, the inertia grows in this form. So we say that the inertia grows quadratically as the mass moves further away from the axis of rotation, right? Where that L, that variable L, is defining the distance of the mass from the axis of rotation. And so one way to think about this is kind of visually would be to think about a figure skater. And so as the figure skater wants to do kind of a sort of twirl within the air, right? So once they jump, what they can do is they can pull their arms in towards their chest. So they're moving the mass closer to the axis of rotation, which is going to decrease the inertia and allow for ultimately for sort of increased angular velocity. And then when they move their arms back out away from their chest, they're going to be increasing their inertia. And that will correspondingly decrease the spin. So now if we go back to our pendulum case, right? So we've got this equation of motion which we've derived, and so if we then apply the parallel axis theorem, we can actually simplify our resulting expression, and we can ultimately arrive at this term, which is pointed to on sort of the left hand side of the slide. So we have the angular acceleration being equal to a gravity term and a motor term, and so based on these two terms, we can then essentially define how it is that this system is going to change over time. Because once we have the angular acceleration, we know how the angular velocity will change, and once we have the angular velocity of the system, we can define how the angle itself will change. And so assuming that our mass doesn't change, and assuming that the length of the pendulum doesn't change, we now have enough information to actually define how the state of the system will change over time. And so one way that we can actually use this, and we can actually compute how the state of the system will change over time, is a technique that's called numerical integration. And so what numerical integration is going to try and do is it's going to use this equation of motion that we found in order to actually update the state over time in a discrete fashion. So in these two equations, essentially, and so one thing I'll point out here is like that again. This state in this case is really the pendulum angle and the pendulum velocity, And then this technique of numerical integration is what's referred to as Euler integration. And so maybe before we sort of talk about some of the characteristics of Euler integration, let's look at what this will actually perform once you've implemented it for assignment 2. So let me step into my implementation. All right. So here is our pendulum environment, and currently there's no numerical integration happening. The pendulum is just spinning in a circle. But what I'll do here is I'll turn on the Euler integrator, and we'll see how it works. So right now I'm going to turn on the Euler integrator, and so now you can see the double pendulum is swinging somewhat like you might imagine physics to actually be affecting the pendulum. But what we noticed, right, is that the pendulum didn't really respect that notion of conservation of energy, because it's increasingly spinning at a faster and faster rate, which would not happen if our equation of motion was sort of obeying the laws of physics that we would expect it to obey. So let's go back and let's look at why Euler integration has this behavior. And so to understand that, really what we were seeing is why Euler integration is not the best choice for implementing our equation of motion. And so the reason why, or one way to sort of think about the reason why, is if we think about this simulation that we just did as an initial value problem. So within an initial value problem, these have been applied across physics and mathematics. And so typically what the setup is for one of these initial value problems is you have some start condition. So this could be time and the current state of the system, like the pendulum angle, for example, or the pendulum angle and the pendulum velocity, where the state of the system is a function of time. And then in addition to this, the setup involves having some differential equation that describes how the system is going to change over time, right? So this is the system dynamics, which is what we had in our equation of motion. And then the question becomes, given this initial condition, how do we estimate the future state based on the dynamics, right, or the next state of the system? And so numerical integration over time is the approach that ultimately we can take, where we know that the difference between the next state at some step in time minus the current state is going to be equivalent to the continuous integral over time of the system dynamics, right? And so Euler integration is an approximation for this true integral. Okay, so what Euler integration did was we discretized time, and we didn't treat it as a continuous integral, but we treated it as a discrete summation, where we were taking sort of discrete steps in time and evaluating the summation over each of those steps. And so the actual implementation of Euler's integration is then shown on the bottom of the slide here, right? So we sort of said that the next state at time sort of n plus 1 or time t plus h would be equal to the current state plus some discrete step size h multiplied by the system dynamics, right? So h here is the time step duration, and then the system dynamics describes the rate of change at this particular point in time. And so what ultimately is going to happen with Euler integration is you sort of get what maybe we could think of as drift within this approximation. And so to visualize this, let's say that we have some function here, and this is and so this function here describes the state of the system on the vertical axis and then time on the horizontal axis. And so if we have some, let's say, initial condition at t0 here, what we then want to do is we want to actually update this. We want to sort of be able to predict how this system is going to change so that we can specify the state at some future time step. So let's say that we want to know what the state of the system is going to be at this time t naught plus h, right? And so within this time step, if we look visually, we can pick out on the function of our state exactly where the state of the system will be at that time. But that's not what Euler integration does, right? So what Euler integration is going to do is it's going to discretize this this change in time, and then it's going to base the predicted next state on the dynamics at the current time, which is t naught. Right? So what Euler integration is going to do is it's going to take what's the slope of the state at this time t naught, and then it's going to predict, okay, based on this slope, based on this rate of change, the state of the system at t naught plus h is going to be shown is like at the red point ending at the sort of end of that slope line, and so you can see it doesn't agree with the true state because of that approximation, and so this is what we were observing in that demo. Is like there was this drift that was being kind of injected into the state of the system as Euler integration approximated that continuous integral. So one sort of shout out that what we could mention is a great textbook if you're interested in more details on how to implement numerical techniques for computing these sorts of integrals. There's this numerical recipes in C book which you could refer to for more details. But let's actually go back and consider this Euler integration over multiple time steps, right? So taken from this particular book is this figure, right, which is illustrating how if we ran through that idea of discretizing the time steps for predicting the dynamics, there's this, you're going to have this accumulation, right? So you're going to have some error at the first step within the Euler integration, and then at time 2 you're going to do the same thing. So you're going to try and predict the state of the system at the next time x3, again based on the slope only at x2, and so you're going to again inject possibly some error at the second step, and this is going to keep going until the error within your simulator builds. So as we look at these types of diagrams to sort of build some intuition about Euler integration, one thing that's important to remember is that this is a second order state, right? So in particular, what that means is that we were modeling the velocity of our system, which was the angular velocity of the pendulum, to be based on the acceleration of the pendulum, right? So in this notation here, the angle of the pendulum is denoted by the variable y instead of theta, like we were looking at before. The angular velocity is y dot, and then the angular acceleration is y double dot, right? And so that the second equation on this line is relating the angular acceleration of the system, or excuse me, to the angular velocity, right? So in other words, y dot is a function of y double dot. And so where this y double dot comes from is where the equation of motion was used, right? So the equation of motion gives us this acceleration function, which we could then use to model the angular velocity. All right, and so the question though still remains of maybe why is the pendulum going unstable? And so let's go back to this figure that we were sort of looking at, and let's actually step through visually each one of these integration steps so we can build some better intuition about this accumulation of error. So we'll look at 4 time steps here, where in this particular figure the true evolution of the state is denoted by the blue smooth line, whereas the Euler integration is going to be denoted by these line segments shown in red. So if we focus on the first step within our integrator, what's going to happen is, so we're going to begin our integration at this point y0, and to do this, we're going to try and predict the state of the system at the next time step based on the slope of the true evolution function, which is illustrated in this left figure by the pink vector, right? And so what Euler integration will do is it'll take this slope, this rate of change, it'll scale it by the time step that we're integrating over, and then it will use those two to predict the time or the state of the system at the next time step. And so in other words, it'll multiply this system dynamics, this rate of change by dt, the time step, in order to produce y sub 1. Based on this, right, so we can already observe that there's this slight accumulation error, which is just like we were talking about in some of the previous slides. But what we'll see now is how this accumulation error is going to, or how this error is going to begin to accumulate and sort of build on top of each other over time, right? And so if we look now at how Euler integration is going to operate at the next time step, it's going to run the same process, but it's going to be positioned at this point in time overlapping with y sub 1, right? So what it's going to do is it's going to base the change, the predicted change in the state of the system at y sub 1 based on the slope at y sub 1, and it's going to accumulate some small error. It's going to do the same thing at the next time step. It's going to accumulate some more error, right? And it's going to keep accumulating this error over time. And so you can see at the fourth time step, we've actually built up what is visually here as a fairly substantial amount of error within our simulator. And so this is what we were seeing within the pendulum example, where the pendulum began swinging kind of uncontrollably, and it wasn't modeling the true state of the system if it had been following the equation of motion exactly. And so this motivates now the question of how can we improve this integration in order to make our simulators robust and useful for modeling the robots that we're interested in. So ultimately, there's sort of two options that we could consider using to improve the integration. So the first option is we could try and just make the time step much smaller, right? And so the thinking goes here that as you approach, as your change in time within the integrator approaches 0, you'd be approaching the exact continuous integral, right? So if our computer can just represent sort of a small enough time step, and if we have enough compute resources to actually compute with that many operations, then we could reduce the accumulation of the integration error this way. And so that is one approach. However, you can look at other approaches to try and sort of save on some of the computational resources. And so the way to do that would be to use a better integrator than Euler integration. And so this now brings us to the next type of integration that we'll be looking at, which is what's called Verlet integration. So Verlet integration is going to follow a similar idea of updating our state of the system based on the variables that we've been talking about, right? In terms of angular acceleration, angular velocity, and so forth. But it's going to be slightly different from the Euler integration that we saw. So for Verlet integration, the key kind of equation is described on this slide here. And so what we're going to be doing is we're going to be updating the position. So in this case, the variable y is going to be, you can think of as being the angular, the pendulum's angle, which we've been discussing. So instead of theta, anywhere where you see y on the slide, you can substitute in theta if you're referring back to the pendulum slides. And so there's an interesting bit of math here that goes into this integrator. In particular, it's this acceleration function a that is kind of key to Verlet integration. And so if we look at that function a, the steps within it are as follows. So the first thing is to recognize that acceleration by definition is the second time derivative of the position or of the angle of the pendulum's angle, if we're talking about angular acceleration. And so if we discretize that second derivative, we could have we could recognize acceleration in this form, which can then be approximated based on the difference of the velocity, right? So in other words, we're breaking the acceleration down into a function based on the velocities, which can themselves be broken down into functions based on the positions. And so at this point now, if you rearrange this just using algebra, you now have an actual equation based on just the position of the system, right? So just variables y without any velocity or acceleration. That is an approximation for the acceleration. And so using this, then we can solve for the next state of the system approximately by substituting in this derived equation for the acceleration into the Verlet integration equation. And so this is the key step for performing Verlet integration. One other important detail, though, is that this particular equation for advancing the state of the system depends on the previous state of the system, right? So in other words, this equation for the second equation on this slide, so y n plus 1 being equal to 2 y sub n minus y n minus 1 plus the acceleration at time n. So this notes the right that we actually depend on the previous state of the system in order for calculating the next state of the system, right? So in other words, there's that y sub n minus 1 term in the kind of middle of that second equation. And so what this means is that it's really important that we initialize the state of the system before we can actually implement this update equation, right? And so the initialized equation there is how Verlet integration gets initialized, and the reason for that is just so that we can actually update the state of the system according to the integrator. All right, so now let's take a look at this integrator actually being implemented. So if we come back to our Pendulum implementation, what we'll do here is I will start the Verlet integrator right now. And so what you'll see here is the pendulum is swinging back and forth. And so in this case, there's a substantial difference from the behavior that we were seeing when the Euler integrator was running. And that difference is that currently the pendulum is not sort of devolving into that unstable state, right? And so another way of saying that is that with this integrator, it appears that the conservation of energy is being held. So in particular, right? So the idea is that the pendulum sort of has some amount of potential energy when it reaches its sort of highest point within the swing, and then as the pendulum swings down towards the lowest point, that potential energy gets converted into kinetic energy, and then as the pendulum swings towards the other end, towards the other highest point within its configuration, that kinetic energy gets converted back into potential energy. But that those terms in total are being conserved, so the pendulum doesn't devolve into that unstable behavior. And so this is great, right? So in this case, the Verlet integration has improved our simulator's performance, which is going to be key for our robot. So now that we saw the Verlet integrator working, it's worth pointing out that in fact the equation update that we were talking about, it actually didn't update the velocity. So one question you might be asking is, how does Verlet integration incorporate an update to the velocity? And so there is an approach that you can use to actually update the velocity at the next time step, as well as the position. For our purposes, we're going to consider this updating of the velocity to be optional, because again that position update actually is a function only of position, right? So in other words, in the pendulum case, that the update of the angle's pendulum, which is again the middle equation on this slide, is a function only of the pendulum's angle. But if you need the velocity, there is this approach that you can use for Verlet integration. But it is a little bit clunky, this optional equation. And so you might be asking then, well, is there a cleaner alternative? So there is a cleaner alternative, and it's an approach called velocity Verlet. So velocity Verlet is one of the integrators that you'll actually be implementing for assignment number 2. And so on this slide here, we're showing the update equation that's defined by velocity Verlet for both position, which is on the first row, and then the velocity, which is on the second row. And so once again, I'll just point out that this integrator, right, it does use a discretization of time, and in addition, for notational purposes, all of the variables y, once again, could be defining the angle of the pendulum, and then y dot would be defining the velocity of the pendulum. And so the other important thing to consider when you're working on implementing velocity Verlet is that the acceleration function within the velocity update, it actually depends on the updated position. And so the order in which you implement these equations does matter, right? So in other words, you want to be sure that you implement the position update, the first equation, before actually implementing the velocity update, which is the second equation, based on that time dependence. So let's look at what how velocity Verlet performs in our simulator. So here we are back in our pendulum environment. And so what I will do is I am going to turn on the velocity Verlet integrator right now. And what we'll see is the pendulum being stimulated once again under the equation of motion. And once again, just like we saw in Verlet integration, the pendulum remains stable and swings back and forth, maintaining the conservation of energy. And so this will be the behavior that you should expect to see on your assignment 2 implementation once you've implemented the velocity Verlet integrator. And so, so the key thing to make sure of is that your integrator remains stable and doesn't diverge into the behavior that we saw for the Euler integrator. So now that we've talked about how we can simulate the single pendulum using these various integrators, let's for a moment let's revisit the planar two-link arm that we talked about as well. So just as a reminder, right? So this was the arm that we saw in some of these diagrams, which are these aerial views of a two-link arm that had 2 revolute joints that could swing throughout its configuration space. So as a kind of practical example, there's a kind of a fun desktop kind of toy that Professor Jenkins has I think in his office. If you're curious and you want to see one of these working, we have a few examples around the lab that we can do. But one thing that's really neat about the double pendulum, as opposed to the single pendulum, is that you can get this chaotic behavior, which we're seeing on this slide. So this is without any motor torque. This is just under the effect of gravity. And so one of the things that's pretty neat about our pendulum environment is that if you wanted to, you actually could add a second link to our simulator and actually implement a double pendulum. And so briefly, we'll kind of go over what this what would be needed if you wanted to implement a double pendulum. But for project 2, it won't be required. So this is sort of optional, sort of extension material if you're curious. So what it would take is we would essentially have to extend our Lagrangian to account for the additional degree of freedom within the second pendulum, and also to account for the additional system parameters like the second mass and then the second link that's attached. And so these slides here just go over some of the math that would be involved if you wanted to extend the equations of motion that we talked about. And so one of the things that might be apparent is that despite this seemingly simple extension on the physical system of just adding a second mass and a second link, the actual equations for motion become substantially more complicated to work through, but they are really, really interesting. So if you're curious about how you could do this, there are these slides here as a resource, but also feel free to come to office hours or during the interactive sessions, and we can talk more about this. It is an interesting extension, but like I said, it's not required for project 2. And so just to show that it is possible, so one of the former students from this class, they actually did implement the double pendulum in their simulator, which was pretty neat. Okay, so once again, so for project 2, we're going to be implementing a single link pendulum, and so in the coming lab section this week, we're going to talk about the stencil for this project and help kind of get started. But the key functions that we are going to be implementing are going to be these numerical integrators, and so within the code, we'll talk about during lab section on Friday about where you can find these and which ones to focus on. But in particular, we're going to be looking at like Euler integration, Verlet, and velocity Verlet, which are the 3 that we talked about in this lecture. And then for next lecture, what's coming up is going to be our lecture on control. So we're going to be looking at a particular type of control, which is a feedback controller, and we'll be focusing on what's called a PID controller, so proportional integral derivative controllers. So thanks for attending this lecture, and I look forward to seeing you this week.